Hello and welcome to this lecture. What we will do today is to continue our discussions on Scilab and consider several applications. The first application I want to study is plotting several Legendre polynomials, and then I will consider the fitting function. Remember, we had done the fitting function using a Fortran program. Scilab also allows you to do the same fitting in a very quick way, and it also allows you to plot all the fitted functions. Then after that we will consider a very important topic, that of Fourier and Laplace transforms. I will only illustrate the Fourier transforms and leave Laplace transforms as an exercise. Now look at your screen. So what I have done, there are many programs that I would like to execute. So what I do, rather than typing directly on the screen, I shall first enter all those commands in a Word file and then copy paste whatever programs I want from the Word file into the Scilab environment. So you will see this Word environment here, okay, and at the background is the Scilab environment. I have a Scilab environment. I have already opened the Scilab Scilab program, and here is my Word program. So if you are using a Linux operating system, then you may use that editor in that Scilab command. When you do an editor in a Scilab command, you can enter all the lines and then you can execute that edited file, that is an SCF file. Or if you want, you can just edit a normal file and save all your commands there and then copy paste all those commands into your Scilab environment. What is the advantage of this copy pasting? See, if you make some mistake, you can go back to your Word file or a edited file and correct it and then go back to the Scilab environment. This is far more effective. So now look at the first thing I want to execute. I want to execute a graphics program where I want to calculate a large number of Legendre polynomials. Remember, these Legendre polynomials are nothing but your angular parts of your wave functions of a hydrogen atom. So now look at this Word file. It starts here x equal to -1 colon 0.01 colon 1 semicolon. What this means? It is a do loop. X values go from -1 spacing of 0.01 colon 1 semicolon. So the do loop calculates values of x from -1 to 1 with a spacing of 0.01. So there will be 201 points. So in Scilab, as I mentioned before, when you do not say anything, the variable is assumed to be an array variable. So in Fortran or in C or other languages, you have to be very careful about your array variable. Here that array nature is implicit in all the variables. So I define my x values, 201 values from -1 to 1. These x values are nothing but cos theta values. The Legendre polynomials are functions of cos theta. Cos theta goes from -1 to 1, and I have generated 201 points on the x axis or the abscissa. Now on the ordinate or the y axis, I want to calculate several Legendre polynomials. The first one is your first Legendre polynomial, which is a constant function. So how do I generate that constant function? For I equal to 1 colon 201, this is your do loop now. Remember, in Scilab the do loop is I equal to 1 colon 201, not comma. So many times even I make this mistake because I am used to Fortran. So everything you type, every character is important. I equal to 1 colon 201 comma y0 I equal to 1.0 semicolon end. So what this does? It executes a do loop for I going from 1 to 201. It calculates the values of this y0. y0 is my 0th Legendre polynomial. Okay. So that is a constant. So the whole function is a constant. It calculates the value of the constant for the first function. Now the second function is yi is equal to x. So that is the second function is the same as x, that is first function was a constant, second function is a cos theta function. Our x itself was cos theta. So the function is cos theta. So the second function or the first Legendre polynomial with this is L equal to 1, that is cos theta. The next one, so this is like your pz orbital. The next one is your dz square orbital. What was that dz square orbital? 3 cos square theta minus 1 divided by 2. So, my y2 function is a function 3 cos square theta minus 1 divided by 2. Here also I have a do loop. So, what is my do loop? I going from 1 to 201, my y2 is defined as 3 cos square theta minus 1. So, that is my next function. The function next to that is 5 cos cube theta minus 3 cos theta divided by 2. So, that is my y3 function. So, similarly y4, y5, y6. So, I have in this particular set of lines, I have those 6 functions I have created. I have created the 6 functions. Then these first y0, y1, y2, y3, y4, y5, y6 actually 7 functions. Now, I want to plot all the 7 functions. So, I want to plot all the 7 functions on the screen. So, what is the command for plotting now? If I plot 2D, actually I can say just plot, but plot 2D means plot in 2 dimensions. There is a plot 3D as well. So, we are not going to do the 3D plotting as yet. So, plot 2D, if I say plot 2D x comma y0 bracket complete. So, it will just plot x and y0, but now I want to plot not only y0, y1, I want to plot all the 7 variables. So, how do I give that plot statement? Plot 2D into bracket x comma, this is a round bracket and now this is a square bracket. So, the square bracket will have all the y coordinates that I want to plot, y0 separated by one space y1, separated by a space y2, separated by space y3, y4, y5, y6, no comma, just separate them by space, square bracket complete, angular bracket complete, semicolon. So, these are all my commands to calculate all the Legendre polynomials, the 7 of them. So, I copy this from my Word file, then I go and paste it in the Scilab executable file. This is a Scilab environment. The arrow means a Scilab environment. I will go to that point and paste all my commands. See what it has done. Now, look at what Scilab has done. Okay. So, let us see how did Scilab, right. I had given all the lines and pasted them. First is executed x from -1 to 1 spacing of 0.01, then it calculated y0, y1, y2 all the way up to y6. Then we gave this execution plot this command. So, it has executed all these. Then finally, when it says plot 2D x comma square bracket y0 to y6 square bracket complete round bracket complete semicolon, it plots your functions. Now, these are now the functions of the plot. So, let us now see whether it has done all right. So, the first function was a constant function, okay. Y was equal to 1. So, this is the first function which is a constant, no dependence on cos theta. Second function was exactly y is equal to x. So, this is my second function, okay. This is my second function. So, what is my third function? Third function is 3 cos square theta minus 1 divided by 2. This is my third function. So, you will see that the third function has one oscillation, the fourth function will have 2 oscillation and so on. So, it has plotted all the 7 Legendre polynomials here, and the advantage of Scilab is you can get a plot instantly. So, plotting is instantaneous. So, you can really visualize whatever work you are doing. In Fortran it is a lot more difficult. You have to do all the calculations, save it in a file, take that file somewhere else and plot it. There are many softwares in Linux which you may want to practice. So, I shall mention to that there is a software called XMGrace. You may want to download that software XMGrace into your Linux system, and XMGrace allows you to plot very nicely. So, I shall not do that XMGrace in this course. So, try to see your YouTube or try to go to the Google and search for your XMGrace, download it and execute it. That I will not do in this course, because we have now only a very few lectures left. So, I will just illustrate the applications of Scilab. So, what we did now, we executed multiple plots using the Scilab. Now, I shall close this window. So, now what I want to do, I want to execute the fitting functions. Remember, we have done several lectures on fitting function. So, what I want to do, this is that execute legendre.sci. So, if you have saved this file using a Scilab editor, you can execute that file. So, what we did, we copied from Word. So, you can also do it this alternate way. So, now what I want to do, I want to execute a linear least square fit. So, this fitting is a very important operation. So, we will use the Scilab program to do the linear least square fit. Okay. So, now look at these lines carefully. So, there are some 10 or 12 lines. So, you have to write it properly so that you can execute it. So, do not worry too much about the algorithm in Scilab, because Scilab is a very advanced software, whereas our Fortran programs were very straightforward, linear least square fit, okay, or a polynomial least square fit, they had unique solutions. So, we have shown you how to do the programming. Now, we will show you how to do the same linear least square fit using Scilab. So, in this case, my data x varies from 0.1 up to 2.1, spacing of 0.2. So, how do I give it? X equal to into round brackets 0.1 colon 0.2 colon 2.1. So, colon gives a range, okay. Do not give a comma here, there will be, if you give a comma there will be confusion. Here there will be 11 points for the value x. So, now y is the data. What is my data? First point is 0.098, second point is 0.31, all the way up to 2.15. These are my 11 points, which is a dependent variable, x is an independent variable. So, I am just going to show you all the commands which are useful for plotting, plotting as well as fitting, fitting first and then plotting. So, now I want to define a function using Scilab. What is my definition? So, this is how you define a function in a Scilab. Function y is equal to ff x comma p, okay. This is needed for my fitting. Y is equal to ff x comma p, comma y is equal to p1 x plus p2 comma end function. So, my fitting function is a straight line. What is a straight line? Y equal to mx plus c. So, what is my m? P1 is my m and P2 is my constant c. So, P1 x, P1 star x plus P2. So, these I have defined a function. So, now the remaining commands now, they are all required for the Scilab fitting program. So, we do not ask too many questions on that, we just have to repeat exactly as these are. So, after I define a function, so next one, this is the criterion function. So, just put slash slash. So, after this ff, I have to define z is equal to y semicolon x, okay, that should be in square brackets, that is a requirement of the software. Then the criterion function, this is a comment card. Then I define function e is equal to g p comma z, okay. I have to define a function e, okay. I have to define a function e g comma z, okay. Then y is equal to z1, x is equal to z2. So, this just you have to give this whatever fitting you want to do, this is a common thing. Then e is equal to y minus ffxp. So, y is your dependent variable and ff is the fitted function. Remember, you are trying to fit a function, okay, p1x plus p2. So, that is my fitted function, y is my original function, okay. So, then end function, because I have defined a new function e, end function. Wherever I define a function, it should be end function. Then I have this given a comment line, solve the problem. So, when you solve the problem, you have to give an initial value of the coefficients p. Remember, your p1 and p2 were two coefficients. So, to find out the fitted coefficients p is a vector now, p1 and p2. So, to start my fitting, I need to give some initial values. So, these two are my initial values, p0 equal to into bracket 50 semicolon minus 100 semicolon. So, this is p1, this is p2. So, p1 and p2, okay. So, remember this semicolon is important. If you do not give semicolon, there will be a problem, okay. So, then I define this again a Scilab function p error, then you write p colon error equal to data fit g comma z comma p0. So, p0 is my starting data, z is the matrix we have defined, g is also a function I have defined g p z. So, this is my, it will execute, then these are again some standard commands. So, when you come up to this point, it has already executed. When you come out of this, it has executed. So, what am I going to do now? I am going to plot x comma y comma minus 1. So, this is the data which we had given, x and y was the data we had given. So, it will plot x and y, minus 1 tells me what is the nature of the points. Okay. You can vary this third variable here. So, this tells you whether your points will be dots, stars, plus signs and so on. So, the third point, the third variable in a plot statement tells you the nature of the graphics. So, first I will plot x and y is my actual data, then I will plot the fitted data is ff is my fitted function. So, that I will use some other notation. So, if minus 1 is a star, 12 will be some other notation. So, you practice all this. Okay. So, this is my function to fit a straight line. So, what I will do? Very simple, I will copy all the things up to this plot 2D. So, this should be allowing me to execute my linear least square fit program. So, I will copy this, then I will go to Scilab environment. I will go to Scilab environment, I will paste all the lines. So, I have pasted all the lines. So, you see this is the execution. So, it executed every, so you can look through, you execute it yourself, look through all that. P0 was defined as 50 semicolon minus 100, this is my initial thing. So, when you give p error, it does the fitting through this, then plots. So, let us look at the plots now. So, the plus points are my original data points, the plus points are my original data points, and the blue straight line is a fitted function, through the Scilab. So, you see that just by following the statements which were given. So, I am able to do this fitting almost in about 1 or 2 minutes. So, to me you should know the logic of fitting the functions, you should know the program logic, but when you want to do something quickly, I feel Scilab is a much better option. So, this is my linear least square fit. So, what I now want to do, I want to fit some other function, I want to fit some other function. So, let us see what that, so I will close this window. So, I want to do 2 more fitting calculations. So, the next one is an exponential fit. So, what is an exponential fit? My x is the same as the old data, then my y is some function, I have taken some arbitrary number of points, I have taken an arbitrary 11 points. So, I am taking this point, these data points, they are decreasing with x. So, I have given it almost like a exponential decay, I am giving a decaying function. So, the only change now here is that y is equal to ffxp, now y is equal to exponential of minus p into x. So, in the previous program my p had 2 values, p1 and p2. Now, this p will have only one value. Okay. This is not a vector, it is not a column vector. So, it is just an individual number p star x. So, again criterion function z is the same, function e this is the same, error is the same. The only difference now that p0 is a single value. Earlier remember I had p1 and p2, now I have exactly a single value. This is the value of the exponent, initial value of the exponent. Okay. Then p comma error equal to data fit g comma z comma p0, p0 is a single number now. Now, plot 2D, I have used the same exactly the same commands. So, I will copy these and paste into my Scilab and see what it is going to do. Copy up to that plot 2D, I will copy, then go to the Scilab. So, before I execute, let me ask you, in the previous program it was P1 and P2, isn't it? It calculated P1 and P2. So, if I just say P and return, it gives these values. Remember, it was y is equal to mx plus c. The previous program p was a column vector. This is y equal to mx plus c, m is equal to 1, 0.01 and constant was minus 0.007. So, now I shall execute the second program. This is the exponential fit. So, just to clarify, this p was a column vector in the previous program. In my next program, p is a single value of the exponent. So, it will understand the moment you give a new program, it will understand that you have changed the variable. What I will do? I will just copy. Okay, no, I should actually paste it. So, let us see whether I paste. There is nothing because I go back, copy all my commands, then I paste it in the Scilab environment. Paste. So, to execute it, see, it has done the execution. The plus signs were my original data. I had purposely given a set of decreasing data points. I fitted an exponential. So, you see it is beautifully fitting through those plus points. So, this is my exponential fit. So, instead of this, there was no constant to that, you see, there was no constant added, just it was e to the minus p x. Suppose you want to fit a plus e to the minus p x. So, you have to give two variables, just as I had p 1 and p 2. So, I can say p 1 plus e to the minus p 2 x. So, when I give two parameters, my initial p 0 should also be two parameters. What I mean is, see, if instead of y is equal to e to the minus p x, suppose I want y is equal to p 1 plus exponential minus p 2 x, two parameters p 1 and p 2. So, here when I define my p 0, I should define two parameters. Okay? So, then it will solve this problem. So, the next problem I want to do, I want to remember we executed a cubic polynomial fit. We executed a cubic polynomial fit. So, now I want to use that cubic polynomial fit. So, this is the fitting function. My x values went from 0 up to 1. I think there are 11 points, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 data points. My y had also 11 data points. Now, I want to fit through this data points y a cubic polynomial. What is my cubic polynomial? So, here my fitting function y is equal to f f x p, this is a cubic polynomial. What is that? Y equal to p 1 into x cubed. So, in Scilab, the cubed is x hat 3. So, this is how I write cubes in Scilab. In Fortran, you would write it as x star star 3, or if you want to be plain, you will say x star x star x. So, it is x cubed. So, my fitting function is y is equal to p 1 into x cubed plus p 2 into x square plus p 3 into x plus p 4 semicolon comma end function. So, this is my fitting function. So, the rest of the comments are the same, y is equal to z x, criterion function e, everything is the same, y is equal to z 1, z is exactly copy this, you do not have to do anything. So, now the only thing you have to change is my p 0, because I had 4 parameters. Since I had 4 parameters, my initial set of parameters should also be 4. So, p 0 is equal to 0.1 semicolon minus 0.1 semicolon 0.5 semicolon 0.1 square bracket complete. This semicolon is very important. I tried many times with a comma, it did not work because p should be a column vector. So, you get a column vector when you give semicolons. When you give semicolons, you get a column vector. So, I give my initial value of p, that is p 0, then data fit g comma z comma p 0, p colon error, execute. So, let us now, I will copy all this into my Scilab. Okay. Let us execute, copy, then go to Scilab environment. So, I paste my new things. So, it did give some problems. Okay. So, it has given some warning. So, warning should not matter. So, it has given me a plot, it has given a nice fit yesterday. So, let us see whether it has given. So, what I will do, since it is executed, let us try to print that p. There will be 4 values of p. So, you see that P1, P2, P3, P4, it is exactly the same program that we did in the class earlier. Why it has not printed, I do not know. So, let me try this again. So, exactly it has given the same coefficient that we obtained through a least square fit, cubic least square fit, exactly as in our earlier class. The coefficients differ a little bit, but it is exactly the same. So, let me try this plot again. See, I still do not know why it did not plot. It should have plotted my fitted function. So, I shall copy and see whether it will plot it. So, it should plot. So, if it has not plotted, so the plot will be somewhere in the screen. Okay, so, let me see. So, this was, yeah, I think it has plotted. This is my exponent, this is my fit. So, it has plotted, it just appeared somewhere else, or maybe it is the least square. So, let me try that again. So, one thing we have to do, keep trying again. So, it has plotted, it is the fitted function. Okay. So, now let me also plot, this is the fitted function. What was my original function? Original function was x comma y. Okay. This is the fitted function. So, this is the plot you see on the right hand side, it is the fitted function. So, let me try again, paste. It just gave a warning, because I think what this warning says is that you just see here in Scilab 6 they are going to make some alterations from my original Scilab 5.5. So, you will have a better version when you download. So, as far as what I will do now, I will just execute. This was -1, this is my execute that -1, close my bracket. So, instead of ffxp, I will just say y here, because I want to plot my original function. So, already on the right side you have seen that it has plotted the fitted function. So, now I want to plot the y data as well. So, you see, lo and behold, okay, it plotted the y data as well. So, I had this is the fitting function. So, what I will do in the next lecture, I will explain about Fourier transforms. So, what I have done in the present lecture, plotting multiple functions we have seen, and fitting several functions using the Scilab fitting program. This is going to be extremely useful, because many of you will be doing lot of experiments. You want to fit curves through your data points, and Scilab gives a very nice algorithm as well as a set of statements to fit curves through your data points. So, I will conclude here, and in the next lecture I will start on Fourier transforms and then also begin molecular dynamics. Thank you.